So I'm not sure if it's understanding. So it doesn't make sense. Of course.
Okay. So I think we can start. Thank you very much for being here. Today we have Martin Millon, who did his PhD in Switzerland and then moved to Stanford for his first postdoc. And today he's going to talk us about the image deconvolution with STAR, which is an application to be used for strong lensing cosmology. So, all yours, Martin.
Yeah, hi everyone. It's a pleasure to be here virtually. Yeah, I'm gonna talk about like image deconvolution mostly, and let's give you a brief intro about like strong lensing cosmology and like give you a bit of the history of why we developed that technique to do like strong lensing with cosmology with strongly lensed quasar. So you see an image here of a strongly lensed quasar. So yeah, I'll start with like showing you like some pretty images of those lensed quasar, and then how you can improve the resolution of your space-based or ground-based data with STAR, and just end up with a few examples like this one that we observed like from the VST, which is a telescope in Paranal. But first, why I'm interested in this problem? What keeps me up at night is like this Hubble tension, where you see like a tension in the measurement of the expansion rate of the universe, the Hubble parameter. If you measure it like from the CMB or like from early probes like the BAO or Planck, you find like a lower value of H0. And like if you make that measurement in the local universe, you tend to find like a higher value. So depending on how you actually like combine those probes, you end up with a tension ranging from 4 to 6 sigma. And this is important result because the Hubble parameter is like this beautiful test, end-to-end test of the lambda CDM. So there is so you can actually measure the content and the energy content of the universe at high redshift in the CMB. And given the lambda CDM, you can actually extrapolate the expansion history of the universe over like 13 gigayear and predict what should be the distance redshift relation now and what should be the Hubble parameter now. And you can actually make that measurement. You can point this telescope, get out there and measure like this distance redshift relation with supernovae, for example. And the two should match exactly if you have a model that could predict the dynamic of the universe or during those 13 gigayears. And what you see here, it's not matching exactly. So there's two possibilities here. Either like there is like a systematic error in one of the two measurements, or like you need to modify the lambda CDM. The lambda CDM is not like a complete description of the dynamic of the universe. So you need as many to rule out the possibility of a systematic error. You need as many independent probe as possible. And what I've shown on that plot is like they're all like somehow correlated. They all rely on some intermediate calibration, except this one, which is the measurements with a time delay cosmography. So how does that work? So we're using like strongly lensed quasars. So you have like a quasar in the background, which is multiply imaged by a foreground galaxy. So the mass of the foreground galaxy is deviating the light, and it forms like these like beautiful like 2 or 4 multiple mirage images of the same object in the background. And like if the background quasar and the foreground galaxy are not like perfectly aligned, you end up with like an optical path, which could be like a little bit shorter or a little bit longer, depending on the configuration. And this leads to a time delay in the arrival time of the photons in the different images. So this is the same plot, but in 2D. You have the background object here, the lens galaxy here, and like 2 different optical paths. And the time delay, which is this quantity tau, is related to this quantity d delta t, which is the time delay distance. And this is actually, it has units of like megaparsecs. So it's actually a distance and it's inversely proportional to h naught. And this is the ratio of distances to the lens, to the source, and between the lens and the source. And this is the quantity that like you are measuring with time delay cosmography. And it turned out like it's proportional to this term here, which is just the geometrical, the difference in length in the optical path. This is just a geometrical factor. And this factor, which is called the Shapiro delay, which is a GR effect, like it's like the time delay that the photon experience when they travel through the gravitational potential of the lens galaxy and when you observe them outside of the potential. So you see often like this like beautiful Einstein cross. You got different like strong lensing configuration. If you place your source, if I place my quasar in the middle of the caustic, so the caustic is this asteroid here, and this is a line of infinite magnification. So the caustics are maps in the lens plane to the critical line. So if I'm placing my source inside the caustic, I'm forming like this beautiful like cross configuration, and I can plot the arrival time of the photons, and given this arrival time, I can immediately predict where the images will form. The images will form at the stationary point of this time delay surface, and will form at the minimum, okay, and at the saddle points of the arrival time surface. So here you will see like those two images arriving first, followed by these two, and then the maximum in the center, it's like the fifth image, which is almost never observed because it's like highly demagnified. So you've got other configuration. Now, if I'm placing my point source next to the cusp of the caustic, I'm forming like this like cusp configuration where this image here is arriving last. It arrives about like 90 days after the three here. And in the fold configuration, now I'm approaching the caustic from the side. You form this configuration, and with this image coming first, followed by those two and this one. So if you want to infer H naught with this system, you need like three things. The first one being, of course, like the time delay. So how do you measure that? Basically, you small telescope, you monitor it like for many years. In this case, it was like 13 years. And you wait that like the quasars in the background fluctuate. So like if you have like matters falling into the black hole, like it will vary randomly. And like you will see the same variation in the multiple image, but delayed by time. And that's what you're trying to measure with those light curves. The second element that you need is this quantity, which is called the Fermat potential, that you can reconstruct by measuring the projected surface mass density of your lens. So you take a high resolution images, for example, with HST, and you try to model the point source position and the arc brightness and everything to reconstruct the mass profile of this galaxy. And the last term, it's a correction factor. It's like this kappa x term, and it's accounting for all the galaxies along the line of sight that like slightly change your time delay, so you need to correct for that. And we've done that so far for like 7 systems. This is the measurement we got. It's based on analytical but physically motivated mass models, and there are more to come. There is only 7 for now because it takes us very long time to monitor those lenses. Here you see an example of the light curve. You need basically like 13 years to obtain the time delays. I mean, now we got them faster, but like back in the days, it was like taking a very long time. And that's why like it was done only like for 7 systems so far. Here you see like the image B was arriving like 36 days before image A. And it seems easy when you see those light curves, you just have to shift and measure the time delay, but here is what like the lens quasars look like from the ground. If you monitor them with like a small telescope from the ground, it's barely resolved. And this is because by definition, like lens quasars are highly blended objects. You've got like the 4 images that are like typically separated by 1 or 2 oxygon, which is like your typical seeing from the ground. And also you've got like the light of your galaxy and the light of the Einstein ring that are blended together. And if you're not correcting for the PSF, and even worse, if you're not correcting for the time variable PSF, because at every observation you will have a different variable, the flux between images and the flux between the lens galaxy and your quasar images get like blended in a different way, and you end up measuring like the seeing over time instead of like the flux, the variation of the flux of the quasar, if you're not correcting for this atmospheric PSF effect. So to extract precise photometry, you need like to measure like precisely what is the flux of the point sources and like deblend the arcs and the lens galaxy. And why we care about like photometric precision. Here, this is, for example, a light curve taken with the ECAM telescope, which is a smaller telescope and a worth seeing. And you see like here, okay, you see the variation in A and B, but there is no clear time delay. And this quasar was also followed with like a bigger telescope with a better seeing. So the Wi-Fi camera on the 2.2 meter telescope. And here you see that like by increasing the cadence and pushing the photometric precision, you start to catch like the sharp and the fast variation of the quasars that you can like easily match here. Okay, so you can actually measure the time delays in only one season very precisely if you are in this regime of photometric precision. And that's why we're trying to improve the photometric precision of your curve, because yeah, it will really reduce the time you need to measure like time delays. And in most quasar, you're actually not limited by the photon noise. You're limited by deblending errors. Like the major problem is like the flux mixing between like the different components of your lens. Any question on so that's the motivation why we developed STAR, like for extracting light curve on lens quasar, but it can also like deconvolve images, use single epoch images, and I will explain how it works. Is there any question first on the cosmology part and on the strong lensing part?
It was pretty clear.
Okay. Okay, so now I'll explain like how like STAR works. So this is this Python package that we developed with Kevin Michalevich and Fredericks and Fred Corbin. This is based on four main principles. The first one is like it's based on a two-channel deconvolution. I'll come back to every of those points. It tries to deconvolve the images to a Gaussian PSF. It's not suppressing completely the effect of the PSF. We're trying to improve the resolution of the images, not go to infinite resolution. It processes all your data at once, so you don't need to align the data, and you process your full time series at once. And it uses wavelet regularization for denoising and regularizing the problem. And it's implemented in JAX. So JAX is this Python libraries developed by Google, and that has like this magical like auto differentiation feature that allows you to take like the gradients of any arbitrary complex function regarding to any input variables. And you can use this to use like gradient informed optimizer and to optimize like problems with like 10,000 free parameters, for example. And it's also like use GPUs to accelerate the computations. So as I said, it's a two-channel deconvolution. So what those two channels mean is like we will explicitly model the point source in one channel here and the extended source in another one. So from your image, you will decide a fortiori where you place the point source. Then you need to roughly plot them. They will be adjusted to the astrometry of the point source will be adjusted during the fit and the photometry as well. And it will also reconstruct the extended channel. Here we are deconvolving to a known PSF. So you can choose a PSF of your output image. So here we choose to deconvolve to a Gaussian with 2 pixels full width half maximum. Because this is a very convenient choice. We're not trying to deconvolve to infinite resolution. This is not a well-posed problem. So you try to improve your resolution. So here, like from the ground-based data with a seeing of like 0.9 arcsecond, you go to a resolution of 0.21 arcsecond, and the PSF of this image is a Gaussian with 2 pixels full width half maximum. And it's not quite at the HST resolution that you see here. Why this choice? why to deconvolve to a Gaussian PSF and not by the actual PSF. So this is because it's introduced aliasing if you're trying to deconvolve to infinite resolution. So here, this is an example in 1D of what's happening if you're trying to deconvolve a Gaussian with your actual PSF. So the end result should be like a Dirac delta function, and you see here. And it works only if you have infinitely sampled signal, or in other words, like if your signal is like exactly centered on your pixel grid. So this is a stable problem only in the limit where you have like your pixel grid is where your data are sampled exactly on the pixel grid. As soon as you've got a small offset between like the Gaussian, or you have like the sampling which is not exactly aligned with your Gaussian, if you try to deconvolve by the full PSF, which is here as like 6 pixel FWHM, you start like introducing aliasing, and you're not recovering the input signal in the deconvolution. So the trick around here is like to deconvolve by a narrower PSF. So you did your data here as a 6 pixel FWHM, you deconvolve with a slightly narrower PSF, and you end up recovering like the position of the true signal. Then the deconvolution is also a Gaussian, but it's a much more stable problem. So that's why we will first reconstruct this narrow PSF. This is the function that I call S of X here. This narrow PSF, you will hear me saying a lot about like this narrow PSF. And when you want to run STARD, you need to first reconstruct this. So how do you do it? You solve this problem. So you basically you take like stars in the field of view, which is like your stellar cutout T of K, and you inverse this problem. So you try to optimize S of X so that if you convolve it with a Gaussian with 2 pixel full width half maximum, you end up with your true PSF. And you optimize like, let's say like 5 or 6 stars in the field of view to reconstruct like a well-sampled narrow PSF. So you can choose to reconstruct it on a higher resolution grid if you want. Typically, you want like a subsampling factor of 2 or 3 to reconstruct this narrow PSF. And we represent this narrow PSF as a sum of a Moffat plus a pixel grid. But the pixel grid is also regularized. I'll come back to this. But the pixel grid like gives you like almost an infinite number of degrees of freedom to reconstruct like a PSF as complex as the James Webb PSF. So how, of course, you can use STAR to reconstruct like the PSF, the true PSF as well. You just convolve it back with a Gaussian. So that's like what I've made here for comparison. If you give like the tiny team PSF, so the HST simulated PSF, so that I have like the true answer in this test, you give like 6 cutouts here to the code, and you try to recover like the actual true PSF. And STARD will optimize like the small shift between the stars. So you've got like 6 different sampling because like the position relative to the pixel grid is random in this like 6 cutout. So you will use like the subpixel information contains like 6 sample, like random sampling of your PSF to be able to reconstruct like the PSF on a grid subsampled by a factor of 3. And like we typically observe that like compared to PSFR, which is just stacking the stars and like interpolating between the stars, and photutil, which is basically doing the same thing, you gain a factor of 4 to 6 in the accuracy of the reconstructed PSF, especially in the center where you really like gain by using this dithering between your stars. And here I'm showing an example in a lower signal to noise regime, where actually like the spikes of the PSF are below the noise level, and you input like 6 stars as well. This is the truth. This is a reconstructed PSF by PSFR, and you see that it really struggled to define like the first airy ring in this regime, whereas stars is actually recovering the center of the PSF pretty well. And you see that like the noise level in the stacked PSF reconstruction is much higher than in STAR. This is because STAR is also having this like wavelet filtering effect that like reduces the noise in your PSF. This is just like a summary of the metric when you're trying to reconstruct the PSF. This is the astrometric precision. It does a very good job. Like as soon as you get like over a signal to noise of 10,000, you end up like pinpointing the position of your star to better than hundreds of a pixel, much better than PSFR. So the different line here are for the solid line is when you subsample by a factor of 3, 2 for the dash dotted line, and 1 for the dotted line. And the other metrics, if you look at photometric precision or photometric accuracy, what's interesting is like you get an unbiased measurement of the photometry if you subsample your PSF by a factor at least 2 here, you see. And like this is the PSF error. So just the true PSF minus the reconstructed PSF for different subsampling factor, and for a subsampling factor of 3, like star is doing better by a factor of like 4 to about 4 here. Compared to PSFR, which is just like stacking the stars. Okay, so I'll come to the third point, which is like the joint multi-epoch deconvolution. What I mean by joint deconvolution is like you will give like data cube to the code. You're gonna give all your exposure at once and all with your PSF. So you will reconstruct the narrow PSF, so this S function for every epoch. If you have like a time variable, if your PSF is like time variable, and you will give like a cube of PSF and a cube of data. You don't align the images because you will leverage like the subpixel information, which is still included in your desert frame. And how does that work? You will solve this like second deconvolution problem. So the first deconvolution problem was inverting this first equation to recover the narrow PSF for every epoch. The second joint deconvolution problem will be to invert this problem for all your DI and SI and recover this f of x model. Okay. And this is a linear problem. Like the convolution and deconvolution are linear in theory, in the limit of like an infinitely well-sampled problem and no noise. As soon as you add noise and pixelation of your data, you cannot invert this equation anymore. You need like, it's a Hilport inverse problem, so you need like some regularization to stabilize the problem. What I mean by stabilize is like removing some local minima and actually like having a convergence that makes sense. So what star is optimizing is this likelihood. So here we will represent our image by a pixelated grid, which is this h of x function that you convolve with your PSF, and a sum of point sources. So we'll optimize at the same time the amplitude of the point sources, the position of the point sources, and a pixelated grid regularized with a wavelet. And like this is the regularization term. This is including an implicit prior on the source morphology, on the shape of this like pixel grid. And you will do that for all your epoch at the same time. So if I summarize, there's this what star optimize. It optimizes like the point source position. So if you've got like, for example, 4 point sources, you've got like 8 parameters to represent your point sources. It optimizes one amplitude for every epoch. So if you got 100 epoch, it's 403 parameters. It optimizes all the shift and rotation between your exposures. So that's another 2 times an epoch. So 200 if you have 100 epoch parameters, or 300 if you include rotations. And all your pixelated background, which is the number of pixels in your original image times your subsampling factor squares. So you typically reconstruct your deconvolved image on a subsample grid by a factor of 2, let's say. So it's for a 64 by 64 cutouts and 100 epochs, it quickly rises like to 17,000 free parameters. And for solving this problem, you basically need gradient-informed optimizer, which are implemented in JAX. So JAX has this like magical function called autodiff, where you could just compute the gradient of your loss function, even for arbitrary complex loss function. So you could use, then once you have the gradient, it's a much easier optimization problem. You can just follow the gradient and use like all the optimizers that are used in machine learning, for example, ADAM. So you could use ADAM to solve like the star deconvolution problem. And also the regularization help regularizing the loss and making like a convex, making it a very convex function. So I'll come back to this regularization. Yeah, so it's using like wavelets, actually starlet, which is a subset of the wavelet function. And what does the starlet does? For example, the starlets, if I decompose my, so the starlets is a basis to represent your signal. And if I take that image and if I decompose it in starlet, I will decompose it, for example, in 6 starlet scale. And each scales will encode like the frequency information and also the spatial information. So the starlet is this like hybrid base between Fourier and direct space, which encodes both the frequency and spatial information. So here you see that in the first starlet scale, you catch like the high frequency region, like the star forming region, and then as you go up the starlet scale, you start catching like a lower frequency feature, like the bulge of the galaxy in this one, like the very low frequency here. So you can use the concept of sparsity to regularize your reconstruction. So the sparsity is a concept where you try to reconstruct your signal with as few coefficients as possible. So for example, a sinusoid is not sparse in direct space, but it's very sparse in Fourier space because you can represent it with only one coefficient. Here we're gonna try to do the same thing with starlet. You're gonna try to reconstruct your signal with as few coefficients as possible. And like this starlet basis is well suited for astronomical objects. You see already that like this image has divergent scale that are catched with very few coefficients in each scale. So the signal will be sparse in this starlet basis. So try to convince you about this. Here I've decomposed my image and I'm trying to recompose it with only the 1% highest coefficient. So I got this image. And now if I do it the same thing with 5%, with the 5% highest coefficient, you get this. So you already start recognizing most of the image. And with 10%, you've got like already a good amount of the feature. So like we're gonna use this property to separate what is a signal from what is a noise. Here you see that like this image has been denoised because like the coefficients in starlit space that are not among the 10% do not contain much noise. So this is what START is using when it applies this like morphology prior, this regularization term. It basically like minimizing the L1 norm of your coefficient in starlit space. So it has this effect of like thresholding and cutting the coefficients that are not significant, that are not above your noise level. And you can tune that threshold. You can set it so that you reconstruct only the coefficients that are above 1 sigma or above 2 sigma above your noise level in your image. So that's a parameter that you need to tune. Yeah, just a quick summary of the 4 points that I mentioned. So it's a 2-channel deconvolution with like the point source and the extended sources. We deconvolve to a Gaussian, and you can process all your images at all. So before I'm showing a few examples, is there any question on the method?
I think everything is clear.
Okay. Okay, so I'll just use like the last like 10 minutes to or 15 minutes to show you like a few examples. The first one is like, of course, my favorite science case, the lens quasars. Here is an example of what you can reconstruct if you give 100 image, so that this is LSST simulation. So every image is like 15-second exposure on the LSST camera. With the pixel size of LSST and a seeing of like 0.8 arcsecond, I think. So this is what one single epoch would look like for like a very narrow quad with an Einstein radius of only like 0.5 arcsecond, and for 1 arcsecond for the Einstein radius and 1.5. So we expect to find like quite a lot of those like very compact systems. And this is what they will look like with LSST. You can run the deconvolution and like recover most of the images. Also, you even recover the central galaxy in this case. Here you start recovering the Einstein ring when you deconvolve your 100 epoch jointly with the corresponding PSF. And once you've done that, you can extract the light curve because, as I said, you have optimized the point source amplitude at every epoch. So you can reconstruct the light curve for image A, B, C, and D. And you see that like you recover like the variation of the quasar. So here I've taken like a real variation of one of our quasar, inputted in the simulation, means you really recover that peak with high precision and relatively good accuracy. If you were trying to do aperture photometry, there's just no hope. Like with this kind of system, you just measure like the seeing variation is dominating over the quasar variation. So you will just end up with flat light curve with no hope of measuring time delays in this example. Fred Dux has applied that to a whole bunch of lens quasar, like 22. You see all of them here. I'm going to zoom in onto some of them. Those are from high cadence monitoring data taken at the ESO 2.2 telescope and the VST telescopes in Chile. So there are like about, it really depends on the object, but like it ranges from 400 observation to 1,000 that you combine together to obtain like high resolution images. So here is, for example, one of my favorite. This is like this Hedron galaxy that you see in Hubble. This beautiful lens, you recover like most of it. Remember that like the PSF of this image is a Gaussian with a resolution of 0.21 arcsecond. Here, 1537, where from one image you don't see any arcs, but if you deconvolve it, you clearly see this Einstein ring like popping out that you see also in HST. This one, 1131, you clearly see that the Einstein ring popping out, the central galaxy also. It's pretty nice. I like this one as well, HE0230, because like the image D is actually forming in between those two like galaxies. So it's like small group forming the lens, and like the image D is here, and you see in HST like it's barely visible, but like these are cosmics probably, but like here you see like one of the lens galaxies, the other one is here. It's barely visible, but like with deep images, like combining 100 of 5-minute exposures on a 2.5 meter telescope, you still recover like almost the same features. Here, it's interesting because here you don't see at all the lens galaxy in the image, but like after the convolution, you see it popping out. And this one is also one of my favorites because you see like the very faint Einstein ring like being catched by the deconvolution that you see in the HST images. And of course, we're happy to have pretty images, but like what we want is like very precise light curve. And Fred has done a great job at like extracting those light curve with this technique. And you see like the signal is very clear here. You like the light curve are well sampled, super precise photometrically, and you even see the time delay by eye. Like here, you see those features that are like match in the 4 light curve for the system. So this will have like a measurement of H0 very soon. So stay tuned for this one. Yeah, just a quick mention of the runtime. If you run it on GPU, like extracting the light curve for about 1,000 epoch, and if you take like 64 by 64 pixel cutouts, it's about 11 seconds on a GPU. You have like 5 seconds of compilation, and then it scales almost linearly with the number of epoch. And for the size of your image, the scaling is even better. Basically, it's still 5 seconds of compilation, and then about like 10 seconds to run like even on a big image with 10 epoch. This is because as soon as you have enough memory in your GPU memories, it's not gonna slow down the code to give like bigger images. At some point, there is a step when you start to overload the GPU memory, but like as soon as you can fit all your data in the memory, it's really fast. Another example with supernovae. Here it's also like an SLSST simulation where I've like created like 50 epochs in total, and the supernovae will explode at the 30th. So you will see it like appearing at some point, I guess, here now. So this is the data cube that you input to the code with the corresponding narrow PSF. The peak brightness is at magnitude 19, and it's like the PSF of those images are made with realistic ground-based PSF taken from our monitoring campaign. So I've used like the real 2.2 meter, the real PSF of the 2.2 meter telescope to generate this simulation. And the galaxy is taken from an image of the cosmos field seen by HST. And there is a random dithering between the images of 0.3 arcsecond. So this is the input that you give to the code, a data cube of 100 image with 64 by 64 pixels, and a data cube of a subsample PSF, so 128 into 128 pixels. You can run the code and you end up with a measurement of your astrometry, of the position of the supernova in the galaxy. You get the point source photometry at every epoch, so the light curve and your deconvolved image. So this is the output of the code. You've got your data, your model with the supernova exploding at some point, and the residuals, and your reconstructed high resolution image. So here is a reconstruction. One LSST exposure, you recover this image compared to the true reference image seen by HST, and the light curve that you extract. It's actually like really accurate, and also like the precision is also much better than like the DIA, so the difference imaging. Even though the difference imaging, you just have also like a lot of images to construct the template and subtract that to measure the flux of the supernova. But the template is reconstructed at like a worse resolution. With STAR, you reconstruct like a higher resolution template. And this is what gives you like this like a really good accuracy. It's because you go on a subsample grid to reconstruct your template before subtracting it from the supernova. And also like I mean, you get an accuracy of a few millimag here, and also like the astrometry is very good. You recover like the precision of the position of the, you recover the position of the supernova to better than a tenth of a pixel. And a last example also with space-based data. So here I'm just using like single epoch. There's just one image. You don't have to give a data cube. You can just give one. Of course, you lose the information that you have like in the desert exposure, but you still can extract and measure the photometry and extract the flux of the point source. So here, this is one field of view and the SMACS J0223 galaxy cluster. And it has like this galaxy here, which is called a sparkler. This is a lens galaxy, so it's like behind the cluster. It's lensed by the cluster, and it's really interesting because it has all these like small spots. Some of them are actually globular clusters at redshift 1.37. So that's crazy that we can see that with James Webb. And those globular clusters are unresolved even with James Webb, so they are point sources. So you can use STAR to extract actually the photometry and of those point sources and deblend it from the light of the cluster and also from the light of the arcs. So that's what I've tried doing here. So you need first a very good model of the James Webb PSF, and this is the original image. This is all the deconvolved image with the point sources. We identified like 18 point sources, which we could extract the flux from in like 6 different bands. So using this, you get like the photometry, the point source photometry deblended in every band. So this is the SED, the flux that we measure. Some of them are probably globular cluster. They are SED compatible with globular cluster. Some of them are just like either the bulge of the galaxies or star forming region. And you see like the former photometry, this is just aperture photometry, like the dotted line. Here you see like big differences, and for some of them, it's because like with aperture photometry, of course, you don't deblend the light from the extended source, like from the galaxy itself. So this is what STAR allows you to do, is like deblending also like these two components between the extended source and the point sources. Of course, nothing prevents you from using it without point sources. So if you want to just deconvolve a single image, single epoch, without any point sources, you could just study for example, the source morphology and deconvolve this like galaxy observed with James Webb. Here you've got a 0.03 arcsecond per pixel. And then if you improve it by a factor of 3, you can get to 0.1 arcsecond per pixel and like start to like have a better understanding of the star forming region and everything. So I will just conclude on a short summary. STAR is like this like fast 2-channel deconvolution algorithm that you can use for extracting the photometry. It's optimized to extract like light curves of blended objects, for example, lens quasar. And we've been using it for measurement of time delays in strongly lensed quasars to measure the Hubble constant, and there are many more coming soon. So we will have like probably like a bunch of new results with the TD Cosmo collaboration very soon. All the examples that I've shown, you can find them in this repository. This is the repository called Start example. You can reproduce all of them and find more and tutorial as well. And you are welcome to, if you want to use it, to participate, open GitHub issues, even pull some, if you want to contribute to the code, like submit some merge request as well. We welcome any contribution. Thank you very much, and that's all I have for today. Thanks.
Thank you very much, Martin. Excellent talk. I think we'll have some questions, starting with Mohammed.
Yes, thank you very much, Martin. About finding the stars, so in the 2-channel process that you separate the point sources from the extended ones, how do you find them, or do you find them on the 64 by 64 pixel crops, for example, or on the larger image?
Yeah, so you're speaking about estimating the PSF, right?
Yeah, in the first phase.
Yeah. So yeah, you identify them like around like your region of interest. So you take a larger image. What Fred is now doing, Fred Dirks, is now querying the Gaia catalogs and looking at like stable stars that match the brightness of your quasar, for example, and that are close by. So it takes like the 5 or 6 closest stars that are like stable photometrically that are around your quasars, and then extract the cutout around those and reconstruct the PSF.
So for that scenario that you said, even if you don't have stars in the image, you're actually using stars from nearby, like the galaxy showed without stars.
I mean, nearby you need an image of them. You need like some idea of what is your PSF, and you do it like empirically if you have stars. If you don't have stars, you can use a model for your PSF. Of course, it's probably less accurate, but yeah, the best is like taking the closest star if you have some.
I'll have some other questions, but I'll wait until to see if others.
Yeah.
Questions? Sorry?
Hi, very nice talk. What if instead of a time series of images, I'm interested in a data cube where the third dimension is the spectral dimension?
Okay, so yeah, I guess in this case, you would expect to have like one PSF at every wavelength.
Yes. Let's assume, for example, that it is JWST data where we have the PSF at every wavelength.
Yeah, I see. The thing is, like, I guess you expect also like your signal to be different in the different wavelengths. Like a galaxy, because let me come back to this equation. Here you're trying to deconvolve like f of x, but you assume that like f of x will be the same across all wavelengths, which is not the case for a galaxy. You probably like observe different size as a function of wavelength. So I don't think it can be used in that way, in a sense. Even if you got like, if now this is different band, your data different band, but like the signal you're trying to reconstruct is going to be variable between band as well. So you should run the code at iteratively at every wavelength. You know what I mean? Like here, the final image is not going to be shared across all band. It's going to be variable across your data cube.
Would it be possible to have the start length based wavelength dependent?
Yeah. What you can do is like you can probably like bin your data. Like if you every like maybe I don't know 100 nanometer or 50 nanometer, you could run a deconvolution. This would work probably.
Okay.
But yeah.
Questions?
Frederick,
Yeah. Frederick, you can unmute yourself and ask.
Yeah. Actually, so I know Martin quite well, but yeah, just a comment about what was said about deconvolving different wavelengths. So completely agree with Martin. Objects change as a function of wavelength, and it's not because you change the wavelength basis as a function of wavelength that it will work, because the morphology is still different of the object itself is different from one wavelength to another. What may be done instead is a joint deconvolution of, for example, Mu's data cubes, and then you have the same setup in terms of wavelength for every epoch, but then the spectrum is allowed to change. So you have at different times the PSF at the given wavelength is the same, but the spectrum changes. So you have some kind of spectrophotometric monitoring of your objects. So the thing is time dependent, but not wavelength dependent. So F is the same at every wavelength, but can change with time.
Just a comment, PSF doesn't change. PSF is changed based on a filter. In different filter, PSF has different shape, different properties, and it's gonna be changed. And it will affect your result if you don't consider it and you are considering the PSF as a constant value. And about the tiny team you are using, I saw many papers they are using for James Webb data. In center, as you showed, it's like a circle, but it's like a flower. How did you fix it? Because for the lensing quasar, the central of the PSF is important, while the shape of the PSF is different with the original star. How did you consider this issue?
Okay, so to your first question, of course, like we're talking about monitoring in a single band. So I mean, in this case, there is just one single PSF, and of course, we are counting for the variable PSF from epoch to epoch. That's like the data cube you give. You also account for like the variation from epoch to epoch of the PSF. To your second question, this is just an example with the tiny team PSF. I could have taken any PSF shape. Where it is? It's here. Yeah. This shape is I know that tiny team PSF is not really matching the HST PSF. It was just like a benchmark test with something complex. I wanted like something complex, and of course, reconstructing the center of the PSF is the most important. And what I'm showing here is like what you see in the center compared to other methods. Like START is doing much better, even at reconstructing the inner like 3 or 5 pixels. And this is due to the fact that you account for the dithering, and like you're not limited by the Nyquist sampling anymore, because you've got a random sampling of your signal 6 times, and there is no limit to the highest frequency that you can reconstruct. If you would have like a regular sampling, like on your CCD, like pixels on your CCD, you will be limited by the Nyquist frequency. But the fact you have like this random shift between the stars, like the stars are not exactly centered on the same position on your CCD, give you the opportunity like to go beyond this limit and like in theory reconstruct like super high frequency signal even at the very center of your PSF. if you account for the dithering property.
Okay. Elena?
Yeah, thank you for a very nice talk and very nice procedure. I was wondering if you tested if there are some issues related to the flux conservation or color measurement with this method.
Yeah, so I've tested the flux conservation. It's conserved to very, very high accuracy, to a few millimag. And also that this is the advantage of this like sparsity-based method, I would say. It's because it's exact reconstruction. Like the decomposition in wavelet and the recomposition is exact. So for example, compared to machine learning technique, also doing image deconvolution, the machine learning doesn't guarantee that you conserve the flux. The wavelet decomposition and wavelet thresholding guarantee that the flux is actually conserved. If you in the limit where you reconstruct like all the coefficient, but you have an exact reconstruction in that sense. So yeah, because like if you use machine learning, for example, you will learn some priors. So you will like, this is my prior. Like a machine learning technique will learn a different one. So maybe a more suited one for galaxies. Like you will learn what are the features that are more likely to be found, but it's not gonna guarantee that like this galaxy that you are decomposed is having an exact solution.
Perfect. Thank you.
Okay, thanks again. So about the time dependency, you mentioned time as an amplitude. So how about the shape of the PSF? I mean, well, like we see in ground-based observation, especially, the full width of maximum changes. But when you just account for it as an amplitude, then the amplitude doesn't change. But depending on wind speed and things, the actual shape of the PSF can change. It's not just a
when I'm giving my cube of PSF, it's a different one at for each frame. Like my data here are matching the PSF that I've reconstructed for this frame. So I've reconstructed the PSF on stars in the same image at the same time. So here it's a different PSF. Every layers here is a different PSF. And when I'm optimizing everything, you see I'm convolving my PSF with my model, and the PSF is variable. And then the amplitude, I'm convolving my PSF by an amplitude, and this parameter varies, like because the object is variable. But this varies because the scene is changing.
So that you allow the shape of the PSF to change in between each exposure?
Yeah. Yeah. At the first step is reconstructing for every epoch, reconstructing a PSF.
Okay, from the stars.
From the stars, yeah.
Okay. And yeah. Any
I
other?
think Frederic had some comments.
Yes, sorry to come in again, but yeah, just a comment on this. So Mohammed was saying you leave the PSF vary between different epochs. So yeah, it's variable between different epochs, but in the sense that it's measured for each frame at any epoch. But once it is known, it's not affected, and it doesn't change during the fit. That's what I mean. And by the way, you could allow for that to correct slightly for the PSF at the same time. But of course, you have more degrees of freedom. And I just wanted to comment as well on, since people are in the room are interested in Arrakis. So Arrakis will have, as you know, 900, I think, or 600 images, all dithered. Objects are not necessarily variable in the field, but if they are, it doesn't matter with stars, as you've seen. But you can consider stars as a way to optimally combine your images as well. So it's let's say some kind of optimal drizzling.
Yes.
And if if point source objects vary in the field, then it will also get you the light curves for free. The only caveat is that the Arrakis images will be 4K by 4K.
Exactly. Yeah, that was what I wanted.
And once subsampled by a factor of 4 or 5, the code will have to be re-optimized.
Yeah.
You need a GPUs with a lot of memory if you want to do that.
Gabriel raised his hand. You can unmute yourself.
Yes, can you hear me?
Yeah.
Yeah, on topic of Arrakis, I was wondering if this PSF reconstruction and deconvolution technique would not work if the PSF is smaller than a pixel, right? Because then you're limited by the plate scale of your image, and the PSF doesn't matter anymore, right? Because I think in the case of Arrakis, it might be the case that the PSF will be smaller than the pixel.
Smaller than a pixel? You
Sampled. I think you mean undersampled, right?
Yes, yeah, you could say it like this, yes.
Yeah,
like
it's smaller
you
than the
mean
pixel.
you have an undersampled PSF. Like, for example, this is the case for the bluest band of GWST and HST, where the PSF is actually like undersampled. You can still reconstruct it. Actually, STAR is doing a good job at reconstructing undersampled PSF if you have many stars, because it does like this. You reconstruct it on a higher resolution grid. If you have only one pixel to represent your PSF, I guess you will need like a lot of drizzled exposure. But is it really the case? You will have only like all the PSF is gonna be just a top hat function in one pixel?
No, it's not that bad. But we are undersampled. Our PSF is expected to be about 1.5 arc seconds, and the pixel scale is 1.3 arc seconds. So, yeah.
Okay, so that's like HST bluer band regime, I would say, more or less.
Yeah, it's slightly a little worse, but yeah.
But it's actually like this framework is actually allowing you to get like a model of your PSF on a finer grid, because you take advantage of like this feature, like you have several stars. Yeah.
Especially the fact that in Arrakis we have 900 exposures, that helps in this case, because we sample the same star, and we're especially in the observing strategy, we're putting a lot of emphasis on random positioning within the dithers. So yeah, that is a good aspect.
And you expect the PSF to stay stable over the 900 exposures, or you might expect it to change?
Mostly stable. Yeah, we don't. ESA has told us that yeah, we can account for very good stability.
Okay, well, that's something you can measure if you split the dataset into.
Exactly.
Yeah, for sure, 900 is a lot for reconstructing a PSF.
Actually, you can do the experiment of having the same star in all the dithers and use this to construct the PSF, and compare to the PSF you reconstruct by using all the stars in one single exposures.
Yeah, exactly.
Of course, in one single exposure, you will have the spatial variations of the PSF as well.
Well, but then a single exposure doesn't have the resolution, so it's very undersampled, a single exposure.
Yes, and so would it be preferable to actually have a worse PSF or kind of defocus telescope to have a better sampled PSF so that we can actually estimate it over time better and deconvolute it better?
Yeah, actually,
radical solution.
No, I'm just asking out of curiosity, because it seems that, I mean, I always thought the PSF of the telescope is the most important thing to have, like the smallest, and yeah. But actually, with a deconvolution technique like this, the knowledge of the PSF is the most important thing to have, because then you can really go deeper than the resolution, and to better sample the PSF and to monitor it, you might want to sample it properly. So in case of Arrakis, it would be not the case, natively at least.
It's funny because Fred Dirks actually, like in the light curve, is still using like the data points that are completely off focus. We've got a few epochs where like the telescope is completely off focus, or like if the telescope have drifted, so you've got a triangle for the PSF, and you can still recover the flux actually. So the shape of the PSF doesn't matter. You made some tests with a triangle PSF. It's the same problem basically.
But remember that in the case of Fred, he also has the other PSFs that are good. So the bad PSF the bad point is constrained by the joint.
Constrained by the rest, yeah. Yeah, but
all the points are all the PSFs are joined. I don't know how it works.
Yeah, but the thing is like the flux, which is measured on a single epoch, even with a terrible PSF, like completely off focus where you see the donut, is actually making sense. But it's just you spread your flux on more CCD, on more pixels, so you just increase your noise. But in theory, it works in the same way.
Now, there is another thing to consider is that the PSF will vary across the field because different stars don't have the same color. So even if the instrument is perfect, different stars have different PSFs, which is why the temporal stability of the PSF will be important for Arrakis, because then you can use the same star at different epochs and still have the drizzling. While if you have to use all the stars in the same field, even if the optical distortions are negligible, there will still be PSF distortion due to different colors of stars.
Yes, that's a good point. Yeah, we only have broad filters. Yes. Maybe one more question. Well, I have two more maybe, but I'll ask the first one. So about the wavelet decomposition, you were showing the orders, the dependency on the orders, and how you add as you add more wavelets, you get better things. In the final image, yeah, in the next one where you showed the different layers. Yes. So in the final one, like for example, in Araki especially, we're really interested in tidal features of galaxies. So I'm looking at the orange, let's say, arc that we see around the galaxy, especially in the real image, and the overdensity in the extended signal that's crossing the bluer line behind. And so when I compare that you know, it's so in terms of the diffuse flux, it has preserved. I mean, this starlet has kept the point sources, but for the extended sources, it's actually made it smoother.
Yeah, because I've got only 10%. If you go to 99%, I mean, if you go to 100%, you will recover exactly the image. Of course, I've thresholded some coefficient. So some coefficient has been cut. So it has recovered only the most significant feature. And the starlets are isotrope, so it will create like stuff that are isotrope first and then try to correct for that. So the most significant coefficient will always be like this like smooth component and then a blob here. And then if I keep adding coefficient, you will start like recovering like small details and like also maybe the low frequency feature that are less significant. So for example, maybe like this thing here, like you will start like having hit, but like maybe it's if you keep more coefficients. Yeah.
And what's the cost of adding more coefficients?
Oh, actually, like here it's very extreme. Keeping only 10% is like very extreme. It's like thresholding your image at like 10 sigma or something. The cost of so you can choose a threshold. If I put a 1 sigma threshold, you probably have like most of the feature. And the cost is the same. It's because I'm not actually thresholding. Like you're optimizing this L1 norm, which is equivalent as a thresholding. Like the optimum of this function is equivalent to do a soft thresholding in starlet space. But what you optimize is this function, and it will converge with the solution that you would have obtained if you would have threshold your signal. So it's exactly the same cost. You just optimize this function for the same price. And what you tune is this lambda parameter. If you put lambda equal 10, you will cut at 10 sigma. If you put lambda equal 1, you will cut at 1 sigma.
Oh, okay. And since time is passing and I don't want to keep too many people, so just about the GPU memory usage, you mentioned that memory is because memory is the most expensive thing in processing. So if you have a 1 megabyte, let's say, well, less than 100 kilobyte 64 by 64 pixel crop, what's the maximum memory usage of the GPU for that crop? You showed the time, but it would be good to also show the memory usage as a function.
Yeah, I agree. I don't have this number for you. Let me find that. Here you've got the number of pixel that you use. So depending on the number of epoch and the cutout, so it doesn't really matter if it's like more epochs and less cutouts or the opposite. And here you see that you have like 7 million pixel, and it fits well in the GPU memory. I guess you could go to pretty high number. Like, I mean, it really depends on the memory of your GPU. If you've got like 32 GB on your GPU memory, you can have a lot. Those are expensive. If you've got a cheaper GPU with only 8 GB, maybe you reach that limit. But I've never hit that limit. On all I never saturated the memory. I think Fred did, but he was really pushing the thing hard. I can ask him at which point he was like exploding the memory.
Okay, thank you very much. I'm done.
Okay, thank you very much, Martin, for the very nice talk and for the discussion. That's all.
Yeah, thank you very much.
Recording.